Section 9.1. We're going to talk about translations. Speaking of translations, different definition of translation. Anybody in here take French? Couple, okay. So two cats were swimming across the river.
Oh, is this a joke?
Cat 1, 2, 3 and cat 1, 2, 3. Which one makes it across the river? No, 1, 2, 3 because 1, 2, 3 cat sank.
Wait, say again? Why did 1, 2, 3 make it across the river?
Because 1, 2, 3 cat sank.
What is 1, 2, 3?
1, 2, 3?
It's French. You speak English, please, and help
This was a joke just for the people that understood French.
Well, what about
So you have to go figure out what 1, 2, 3 cat sank means.
Can you just tell us?
Well, that ruins it. All right. All right, a transformation. We decided with our opener that a transformation is just a change. We're going to change a geometric figure somehow. I'm going to say change a figure somehow. And we're going to talk about some specific kinds of transformations. The ones we're interested in for the first part of our chapter are what we call rigid transformations. What would you guess we mean when we talk about a rigid transformation? What do you mean when we say something's rigid?
Rough.
Rough, stiff. Rigid means stiff, firm. So a rigid transformation is a transformation that doesn't change the size or shape. So we're not stretching or bending our shape at all. So we have three of them. And then at the end of the section, end of the chapter, we'll talk about one special kind of translation that's not a rigid transformation. We'll talk about a translation. That's what we're going to talk about today. A translation just means we're sliding our shape around. So we're just kind of moving it around. We can think of it as a slide. We're going to talk about a rotation. Pretty self-explanatory what it does. Rotation rotates. And several of us talked about rotations on the opener. And we're also going to talk about a reflection. And a reflection reflects or mirrors. And we're talking about thinking about like a flat mirror, not a carnival mirror. Our rigid transformations don't change the size or the shape of our figure. So the technical way we say that is they preserve distance and angle measure. Yeah, what we mean by they preserve distance is they don't change the lengths of the sides of our shape. So they're not stretching. Those are the distances we're talking about, the sides of the shape. They're not stretching or compressing the sides, and they're not stretching or compressing the angles. So all the sides, all the lengths, everything stays the same before and after our rigid transformation. So what we do with these rigid transformations is we set our everyday definition so far of congruent has been same size and same shape. That's how we tell things are congruent. And then we had some specific rules for triangles, for polygons, that kind of thing. We said we'd make it a little more technical later. Well, this is where we make our idea of congruent shapes more precise. Shapes are congruent if one is a rigid transformation of the other. That's going to be our more technical definition of congruence. That's how we tell if they're the same size and same shape. Can one be a rigid transformation of the other? All right, are we good so far? So this first part is just kind of introducing the idea of transformations and the way we're going to talk about them. All right, we call the original figure is the pre-image. And then after the transformation, we get the image. So in our book they use pre-image and image. We can just say the original and the image, but you should know that when they talk about the pre-image, they mean the original shape. All right, so the first thing I want to do is look at some examples. I want to say, are these rigid transformations? Just by what they look like. So here's my first one. It's not going on. This. Is that a rigid transformation? No? Why is it not a rigid transformation? Change the size. So that would not be, just by what it looks like, that would not be a rigid transformation. If we're talking about it only moving on the screen. How about how about that? If I did everything perfectly. If I drew everything perfectly, this could be, yes, what do we do to the shape to get from here to here? Moved it over and down, right? And in just a little bit, we'll talk about, well, what do we mean when we say we slid it over and down? We can talk about how much over, how much down, and make sure we do exactly the same thing every time. All right, let's look at this one. Let me start over. I'm trying to do my drawings really nice. And how about this? Does that look like it could be a rigid transformation?
Yes.
Yeah? What could we have done to this one? Could be a rotation or a reflection. Could it be some other combination? How about if we rotated this and then slid it down? So it could be a rotation and a translation. So it could be some various combinations of these rigid motions. So this is what we mean when we're talking about rigid motions. Can we do some kind of thing to move the shape on top of so it turns into the other shape? All right, we good so far? Okay. We use arrow and prime notation for transformations. So for example, we would say triangle ABC is the transforms to triangle A prime, B prime, C prime. We could say this several ways. Triangle ABC transforms to triangle A prime, B prime, C prime. Triangle A prime, B prime, C prime is a transformation of triangle ABC. Or we could say triangle ABC maps to triangle A prime, B prime, C prime. So if we were looking at a picture, say I have this triangle ABC, transforms to triangle A prime, B prime, C prime. So here's my picture, here are my triangles. So we would say that triangle ABC is the image. Triangle A prime, B prime, C prime. So triangle ABC is the pre-image. Triangle A prime, B prime, C prime is the image. Angle A transforms to what angle? A prime. That's what this tells us. A transforms to A prime. Segment BC transforms to which segment? B prime, C prime. So each point in the pre-image transforms into some point on the image. Each segment on the image transforms to a segment on the pre-image. Each angle transforms to an angle, etc., etc. We could match up all the different pieces of these two triangles. And since a transformation, a rigid transformation, doesn't change distances and angles, what would we say about these two triangles? If the sides, corresponding sides are the same lengths, corresponding angles are the same angle measures, what would we say about this triangle? They're congruent. Rigid transformations keep the figures congruent. All right. Questions so far? Okay. So let's define a translation. That's the main transformation that we want to talk about today. Translation is a transformation and it's a rigid transformation that maps. And maps is just another way of saying takes or moves. All points of the figure, the same distance, in the same direction. So we write this as a T, T for translation. the translation of triangle ABC equals triangle A prime, B prime, C prime. And we'll talk about how we tell exactly how far and exactly what direction that we move things. And all corresponding sides and angles are congruent. So we can match up all the sides and all the angles, and they would all be congruent. All right, so let's talk about how we decide, how we show exactly how far that we're moving one shape to another when we're doing a translation. So the way we will see this written, are we good? Are everybody good with this? All right, the way we'll see this written is translation, T for translation, and you'll see numbers in a little bracket. So this is a translation of triangle RST. What this tells us is how far to move things in the X direction. And this tells us how far to move in the Y direction. So this tells us to move 3 units left, just like when we're graphing coordinates. -3 is 3 units left, and 4 units up. So this would be 3 left, 4 up. So if triangle RST, if R was the point 1, 2, S was the point 4, 1, and T was the point 1, -3. To find R prime, we're going to move 3 units left and 4 units up from here. Well, this tells us exactly what to do with the X coordinate and the Y coordinate. This says subtract 3 from the X, add 4 to the Y. 1 minus 3, 2 plus 4. So I get the point -2, 6. If I move 2 left, if I move 3 left from here, I get to -2. If I move up 4 from here, I get to 6. S prime. It says move 3 left, 4 up. So I'm going to do 4 minus 3 and 1 plus 4. And you get the point 1, 5. And then T prime, do the same thing to T, so we're going to do 1 minus 3, and -3 plus 4, 3 left, 4 up, and we get the point -2, 1. And we could graph these two triangles. If the problem asks us to graph the two triangles, we would graph them, and we would see that one triangle was moved 3 units left and 4 units up from the other one. Just moving each point using the rule that this tells us. All right, questions there? Okay, let's do one where we go the other direction. See, we have two triangles and we have them graphed, and we want to find the rule for the translation. So let's say we have triangle LMN here, And I know my graph is not necessarily going to be to scale. So let's say that's at point -5, -4. M is at the point -2, -3. And N is at the point -3, -1. And then we're going to translate this and I know my drawing's not perfect. Let me just move that up. That'll look a little better. L prime is the point 1, -1. And let's say that M prime is at the point 0, and N prime is at the point 3, 2. So this should be on the axis, so I could redraw my axis here if I wanted to. But we'll just say this is at the point 4, 0. All right, and we want the translation rule. So what are we gonna do here? How are we gonna figure this out? So all this, what this is asking us is pick a vertex and figure out how far left and right, how far up and down did it move. So let's pick a vertex. Which vertex do we want to pick? We'll pick L just because it comes first. How far to the right do we move to go from -5 to 1? 6 units. So we go 6 right. How far up do we go from -4 to -1? 3. 6 right, 3 up. So essentially, that's our translation rule. If we want to make it more formal, we would say the translation 6, 3 tells us to move 6 right, 3 up of triangle LMN equals triangle L prime, M prime, N prime. 6 right, 3 up. That's what this tells us. Translation, 6 right, 3 up. Questions there? All right. Just another way to think about this, maybe to connect a little more with a day-to-day example. Let's say you leave your house and you go 2 blocks east. Two blocks east and 5 blocks north. To the store. So you leave your house, you go this distance, and from the store, so from there, you go 4 blocks west, and then 1 block south, to your friend's house. How far are you from home? So what are we going to do here? we could make a graph. That would work. And the x could be the east and west, and the y could be the north and south. So you can make a graph. That might help you. Can we just think it through? So we're going to break it up. We're going to look at the east-west part and the north-south part separately. So if I go 2 blocks east and then 4 blocks west, what have I actually done in total? Total, at the end, if I go 2 east and 4 west, I have gone 2 blocks west. And then if I go 5 blocks north and 1 block south, what have I done in total? 4 blocks north. So that's how far I am from the house. 2 blocks west, 4 blocks north. After all this walking, that's what I've done. And that's what translations are telling us, is after we move things around, what have we done? We move left or right some distance, we move up and down some distance. And the translation rule makes sure that we're moving the same distance in the same direction. Everything is moving 2 blocks west, 4 blocks north. So you're not moving your feet 2 blocks west and 4 blocks north, and your left hand 8 blocks north and 7 blocks west. Everything's moving 2 blocks west and 4 blocks north. If you did that, you'd have to stretch yourself. That's why we call it a rigid transformation. You have to stretch yourself. All right, questions? Okay. So 8 through 32 even, Common Core and Algebra review. Do block day. And our project a week from Tuesday. And your sketch is due block day.